Welcome to the Explainer. Today we're diving into principal component engineering, specifically looking at insulation and overvoltage protection. It's a high-stakes reality out there. Every single power transformer you'll ever spec or see out in the field has a strict, uncompromising checklist of hardware standing between its core and total destruction. We're talking about lightning strikes, switching surges, or even just a failed gasket that could literally bring down an entire electrical grid. It's an intense environment, and understanding how we protect these massive machines is absolutely fascinating. Okay, let's dive into this checklist. Think of this external hardware as a dedicated team of bodyguards. Inside a transformer, you've got a highly vulnerable $50,000 plus magnetic core and these tightly wound coils. But outside, you have the wild, unpredictable forces of nature and severe electrical grid transients. The components we're about to explore are specifically engineered to sacrifice themselves or to just clamp down on dangerous anomalies long before those forces can ever reach the winding insulation and cause a catastrophic, incredibly expensive failure. So let's look at our first line of defense, the bushings. By definition, bushings are insulated exits. They're engineered to let a high-voltage electrical lead pass safely right through the grounded steel wall of the transformer tank. And you really have to remember, that tank is grounded steel. If the energized lead gets too close, the electricity will arc directly to the tank. So the bigger the voltage you're dealing with, well, the longer and fatter the bushing has to be to give you enough insulation distance. Because if a bushing fails, you've got a direct catastrophic fault to the tank wall, and your transformer is instantly taken offline.
Now, what's really interesting here is how we handle massive overvoltage, like a direct lightning strike. On one hand, you've got arcing horns. These are deliberately designed as a weak link in the system. They're essentially just two metal points positioned so that if a surge overwhelms the insulation, the arc jumps between these horns in the open air, rather than punching through the bushing or the winding insulation. They're cheap, they're sacrificial open-air spark gaps, and honestly, they save a $50,000 unit from a catastrophic bushing failure. But on the other hand, we have surge arresters which do the exact same job, but with incredible precision. A surge arrestor uses a metal oxide varistor. At normal operating voltages, it acts just like an open circuit, totally invisible to the system. But the exact instant a massive voltage spike rolls in from lightning or a switching surge, it conducts hard. It clamps the spike down to a safe level and safely dumps that dangerous energy directly to ground, all before it ever touches the delicate winding insulation. All this protection leads us to our next major engineering choice, which is where we place the transformer and how we house it. We've got a strict divide here based on the environment. First up, we have dry-type transformers. These use air or cast resin insulation and skip oil entirely. And hey, no oil means no tanks to leak. Then we have hermetically sealed tanks. These are fully oil-filled and completely gas-tight. Oil is a fantastic medium for cooling and insulation, and since it's hermetically sealed, there is absolutely no room for the oil to breathe or absorb moisture from the outside air. That makes them the ultimate go-to choice for outdoor distribution transformers that need to sit out in harsh weather and give you decades of maintenance-free service. I want to pause here for a second and pose a quick check question to test the real-world engineering logic we just covered. If oil is such a fantastic insulator and cooling medium, why would we ever choose to put a transformer indoors using dry-type insulation instead of just using a standard oil-filled unit? Take a second to think about the physical realities of the materials we're dealing with here. Well, the answer comes down to strict environmental safety. Oil is inherently flammable, and if a tank ruptures or leaks, it is incredibly messy and hazardous. Think about it. When you're placing a transformer inside a hospital or a commercial basement, having hundreds of gallons of flammable oil sitting in a steel box is a risk that simply cannot be tolerated. You absolutely do not want a massive indoor oil slick next to an emergency room generator. So engineers specify dry type for transformers for indoor use. Sure, you trade away a little bit of cooling performance, but in return, you completely eliminate that fire and spill risk from the building. So the crucial point is this. We've successfully built a robust first line of defense. We've got our bushings providing safe, insulated exits through the grounded tank. We have arcing horns acting as sacrificial spark gaps, taking the hit so the transformer doesn't have to. We've got surge arresters standing by to precisely clamp massive voltage spikes to ground in a fraction of a second. And of course, our tank selection, choosing between dry type for indoor safety and hermetically sealed for rugged outdoor longevity. Every single one of these components is carefully engineered to protect the vital winding insulation inside, ensuring that a single random lightning strike doesn't plunge an entire neighborhood into darkness. But you know, our checklist isn't totally finished yet.
We've talked about keeping massive surges out, but what happens when things start to slowly go wrong on the inside? Next time in part 2, we're going to explore the internal monitoring systems. How does a massive sealed steel tank actually breathe? What exactly is a conservator tank or a Buchholz relay? And how can it quite literally smell trouble and warn you long before a fire or explosion happens? And how do tap changers adjust voltage on the fly without ever interrupting your power? Keep this first line of defense in mind, and I'll see you in the next explainer to finish the checklist.